Oh. Okay, so we're going to talk about numbers. In physics, we deal with a lot of numbers that kind of have extreme magnitude, either very large or very small, and that can be a bit of an issue. Let me just give you an example. Say the mass of the sun in kilograms. If we want to write this out, I'll just have to continue. Okay, so that is the mass of the sun in kilograms. You can see is a very large number, and looking at this, you'd really have no way of even making sense of it, other than maybe just counting the number of zeros, which would take a while. You can see writing this, I actually ran out of room, and imagine doing calculations with numbers like this. And at another extreme, let's look at the mass of a proton. So the mass of a proton in kilograms is that number. Oh, by the way, if you're looking here, this is 199 with 28 zeros after it. The proton, we have 0, decimal point is here, and then we have 26 zeros, and then 167. So, again, we need to have ways of dealing with, these are realistic numbers that we deal with in physics. So we have to have some way of writing them down, like reading and writing and doing calculations with things like this. Can also save money by coming up with a better way. I think doesn't last long, so probably used half a marker just writing that down. Okay, so we have kind of 3 different ways of dealing with either very large or very small numbers. Listen, I'm going to start with prefix. I'll just make a list though. Okay, so the 3 ways that we have with dealing with very large or very small numbers, we can use a prefix, change a unit, or write it in scientific notation. So we're going to go through each of these methods, and we'll start with prefixes because I have them written down here. Yeah, something that I don't think I've mentioned yet. But when it comes to memorizing things, you don't have to memorize too much. Like, for example, you will have an equation sheet which you can use on exams. Then there's equations and things like this, like constants or these prefixes. You don't need to memorize those. So you don't need to know this table. You'll have basically this exact same thing on your equation sheet already. But we have to know what this means. So we have, each prefix has a name and a symbol and a value. And I drew this line here because you notice everything above the line is bigger than 1, everything below the line is less than 1. And they basically go by multiples of 3, like 9, 6, 3, minus 9, minus 6, minus 3, and then there's centi, which is, seems out of place here. And what they've done is they go in multiples of 3 unless you're in between 3 and negative 3. There's actually a prefix for 10 to the second power, or just 10 itself to the first power, and 10 to the negative 1. And maybe you kind of see these used in chemistry a little bit, but they don't do much good, in my opinion. So I wouldn't even bother including them at all. But I did include centi for one reason. You may have guessed, centimeter. So yeah, like let's look at centi. 1 centimeter. So this C for centi, that's just equal to 10 to the minus 2 meters. So 1 centimeter is 10 to the minus 2 meters. I don't like negative exponents, so if you multiply this by 100, you can also write it like this. 100 centimeters is equal to 1 meter. Okay, and so this can help you write down, like, say we have a number, we measure something in meters, so that's our basic SI unit, say 0.054 meters. And we can convert this to, or we can rewrite this using centimeters. We can write this as 5.4 times 10 to the minus 2 meters. Because multiplying by 10 to the minus 2, that's just dividing by 100. So 5.4 divided by 100, that'd be 0.054. And so this is 5.4 centimeters. 10 to the minus 2 is centi. And this table that I wrote down is incomplete. I could actually include another one, tera, because this one is actually used, you might have even heard of this before. Where you would probably hear this is with computers. You might hear, like memory. Your computer your hard drive might have 1 terabyte of memory. That'd be 10 to the 12 bytes. I should point out in computer, because it's based on binary, it's, a little different than what we're doing here, but, not significantly. But yeah, tera, or there's also like teraflops, like how fast your computer operates. A flop is what does that stand for? Like a floating point operation per second. So if it has like 1 teraflop, that would be 10 to the 12th operations per second. So obviously very fast. And that one is in common use, so we don't use it often, but I'll put it on the table. And yeah, if you just look at the letters themselves, like each has a symbol. Everything above the line is a capital letter. Hard to tell with K, but it's capital. And below the line, we use a lowercase letter. Now, we have milli and micro, which both start with M, so this is a Greek letter mu for micro. Okay, so you can use prefixes to handle large and small numbers, and the idea is to get a reasonable number you can write down. Like, I would prefer to see 5.4 centimeters than 0.054 meters. This just looks more compact and easier to read. And I think, if you visualize what a centimeter is, maybe like like 1 digit of your finger or something. That's a little too much, but yeah, but you can kind of have an idea of what a centimeter is. That one, it's a little bit harder to see. Like, try to imagine 0.054 meters. Not so easy. So, yeah, the idea is, because these come in multiples of 3, you can usually write something down where it's, you've got either, like 2 or 3 digits and then a prefix. So let me give you another, see if I can come up with another example. Well, let's just say 9,200 meters. All right, we can write 9,200 as 9.2 times 10 to the 3rd power. And 10 to the 3rd, we can see, is kilo. So this would be 9.2 kilometers, which we just shorten that word to kilometers. So again, that's a much easier thing to read than this. And as long as you're kind of in this range, your numbers between 10 to the 12, and it goes below -9 as well. But as long as you're like in that range, a prefix is often a very good way to go in writing down your number. So I should probably do one more where I use, oh, and I did use centi. I'm trying to think of like an actual physical example. That would make sense. But yeah, I use one above the line and one below. So yeah, just switching to a different, like using a prefix can usually make your numbers look much more reasonable. But they do have limits. I mean, you can always expand this table, and it does go significantly in both directions, but, you know, there's no point in using a prefix if the people if you're writing it down, you're trying to tell someone information, and if they don't know what you're talking about, not very useful. So it kind of loses its use when the table gets too big. So if it's outside that range, we need another way of handling this. So let's move on to change unit. Like, what does that mean? Let me give you an example. Say we've got our solar system. Like, here's the sun. Here's Earth. Like our orbit, Earth's orbit. And here's the orbit of Mars. I'm going to look up the radius of Mars' orbit in meters. Let's see. This is coming from NASA. You can probably trust them. Say 2.28 times 10 to the 11th meters. Okay. So that would be the radius of Mars' orbit. Now, if I told you, if the distance from the sun to Mars, 2.28 times 10 to the 11th meters, does that make much sense to you? It's just a huge number. I mean, I'll bet if you went around telling random people, if you change that times 10 to the 11th, or... actually, we haven't really talked about exponents too much. Let me write this. In... we've talked about prefixes. We could write it this way. 228 gigameters. Now, again, this is one of those things, you tell people this, or just write out the whole number. It doesn't really make much sense intuitively. You could probably make up a completely different number, and no one would even know the scale was off. Like, if you put an extra zero here, people would be like, okay, fine, These numbers are kind of meaningless anyways. And so what I mean when we talk about changing the unit, a meter is just some kind of arbitrary standard that we picked. We just said, okay, that distance is a meter. And, why would we compare some kind of arbitrary distance to the orbital radius of Mars? A more sensible thing to do, I'm going to write this down. I'll use the same prefix. The radius of Earth's orbit is about 150 gigameters. And now, by comparing these numbers, that gives you a much better perspective. You can see the radius of Mars is, a bit more than that. But what we do is we define the distance from the sun to the Earth to be 1 astronomical unit. So I'll write that down instead. So 1 astronomical unit, that's the distance between the Earth and the sun. That's 150 gigameters. And so if we want to know the radius of Mars' orbit, in terms of astronomical units, we'll get a very reasonable answer. So we'll just call that R. I'm just going to give you the number. We'll talk more about how we convert these things. But that'd be around 1.5 astronomical units. And so if you know what an astronomical unit is, it's a distance between the Earth and the Sun. If I tell you the orbital radius of Mars is 1.5 astronomical units, you can immediately create a picture of what Mars orbit looks like. It's, distance from the Earth to the Sun, just go an additional half of that distance, and that's where Mars would be. And so using a unit that's more appropriate for the particular problem that you're working on. If you're looking at like an atomic scale, we often use a unit called an angstrom, which is like 10 to the minus 10 meters. And that's a good measure, like from the nucleus to an electron's orbit or something like that. Now, if you want to talk about distances on an astronomical scale, like what's the distance from Earth to like some distant star, you'd use either light years or parsecs. And so like a light year is just the distance that light will travel in a vacuum in 1 year. And so if I say the closest star other than the Sun is a little bit more than 4 light years away, you get kind of an idea of, if you know that. Like if I tell you a star is 10 light years away, you're like, yeah, it's not that far. Nearest star is 4. It's obviously more than twice as far as that. But that's still a very close star. And so just using appropriate units. The SI units, we have these base SI units. It's important to have those, but sometimes you want to change to something that fits the problem a little better. Now, I will say one thing. When it comes to doing calculations, you usually want to switch to base units. So like if you want to calculate something that involved the orbital radius of Mars, you want to convert this astronomical unit into a meter. Like the radius back into meters in order to actually do calculations. But when it comes to just communicating information, using appropriate units is often the way to go. Oh yeah, so I use a few examples with distance. Another very important unit is an atomic mass unit. I'll write it down. Numerically, it's 1.66 times 10 to the minus 27 kilograms. And what that basically is, it's roughly the mass of either a proton or a neutron. Protons and neutrons have very similar masses, and so that's roughly you can think of that. So if I tell you there's a molecule that has a mass of 36 atomic mass units, you have a really good idea of what size it is. It would probably consist of about 36 nuclear particles, protons or neutrons. Like ordinary matter is made out of protons, neutrons, and electrons. An electron's mass is so small we usually just ignore it. So using for mass, we have an atomic mass unit. Another important unit of mass would be a solar mass. Let's call it MS. For mass of the sun, that's around 2 times 10 to the 30th power kilograms. And so if I tell you there's a star that has a mass of 3.5 solar mass units, it's about 3.5 times as big as the sun. At least in terms of mass, not in terms of volume, but in terms of mass it would be. And so these, just using them, giving you a number, these very large and very small numbers, unless you have really good intuition, like you work with them a lot, not very useful information in terms of just giving you a mental picture. But yeah, using something like atomic mass unit or solar mass or an astronomical unit, these will give you a much better way of visualizing things. And they'll give you much more reasonable numbers. To say like something like 3.5 solar masses, the number just 3.5, that's a very reasonable number. Instead of having like 7 times 10 to the 30th kilograms, that's much harder to picture in your mind. So that's a very good way of doing things, just changing the units to something that's appropriate for whatever problem that you're working on. And finally, we have scientific notation. And the great thing about scientific notation is it works. I mentioned we have big numbers and small numbers that we deal with. But if we're using numbers in a kind of traditional sense, like we typically use them, scientific notation is big enough for absolutely anything that you want to write down. Now I had to be a little careful how I worded that. I said, using it in the traditional sense, like counting and whatnot, like real world problems, scientific notation is good enough, or at least like what we're going to be doing. But we can even run into a problem with scientific notation in more advanced applications. Their numbers are even too big for scientific notation. But yeah, for anything we're doing here. So let me give you, let's describe what scientific notation is, first off. So in scientific notation, it looks like this. So these blanks are numbers. So you always, okay, this is a number between 1 through 9. And the rest of these can be any number you want. So basically, these are all just ordinary numbers, except for the first one cannot be 0. You like something like this, 0.623 times 10 to the 7th power. This number is not written in scientific notation because it starts with a 0. Now, you could write it this way. As, 6 point, it's the same number, just written differently. This one is in scientific notation, this one is not. So it's not a big deal that you can't start with a 0. If you want to express your answer in scientific notation, you can just always change the decimal, or the exponent here by 1. So that's what scientific notation is. And this is good enough to handle any kind of number we'll ever want to even think about dealing with in this class. Now, I like to give an example in like an actual class with student feedback, like in a classroom. This is a great question. The number of atoms in the known universe. So I'm going to explain that number is 10 to the power x. What is x? Well, this is a multiple choice question. I'll make some stupid numbers like 10. Well, that's kind of ridiculous. 10 to the 10th power, that'd be a 1 with, that's 10 billion. We know that there's more than 10 billion atoms in the known universe, but let's go, let's say 1 million or 1 billion. So again, the question is, what is x? So we're talking, what is the exponent here? Is it 10 to the 10th power? That's just 10 billion. I mean, people have more money than that. There's obviously more atoms in the universe than that. But is it 10 to the 10th, 10 to the 100th, 10 to the million, 10 to the billion, or more? I'll add that option, hopefully. Yeah, you can see that. Okay. So I give a multiple choice question, and students usually pick one of these two. And I'm asking, which of these answers is closest to the correct answer? Okay. students usually pick this because our universe is enormous. I mean, the number of stars in our galaxy is more than you could count in your entire life. That's all you did in your life is count. You would never count a number as high as the number of stars in our galaxy. If you had like maybe a few lifetimes, you could do it, like 4 or 5 lifetimes, depending on how much time you spend actually counting. But, I mean, again, just our galaxy is enormous. And stars themselves are enormous things that have, I mean, actually, like a glass of water has more molecules of water, or there's more atoms in a glass of water than there are stars in the Milky Way galaxy. If you think a glass of water, we're already dealing with a huge number of atoms. And then, you know, like a solar system, like our solar system, which is mostly just the sun in terms of mass, you know, the number of atoms is just hard to even imagine. And then our galaxy has, you know, just this more stars than you can count. And the number of galaxies in the known universe is around the same as the number of stars in our galaxy, which is around 100 billion. Well, it's, I think, closer to 400 billion, but, you know, what difference does it make? But anyway, so obviously we're dealing with an enormous number, and so people pick these as their answers. These are the exponents. But the correct answer is B. And when I say correct, I mean this is the closest to the actual answer. This is actually too big. The number of atoms in the known universe is around 10 to the 80th power. So this is an enormous number. That's the thing with scientific notation. It can be a little deceptive. This doesn't look all that big, but it's enormous. It's hard to even imagine something like this. And so if you can write in a very short way the number of atoms in the known universe, we're not going to have to worry about running out of, you know, having to deal with large numbers in scientific notation. It's big enough to handle anything we can come across. So that's one of the great advantages of scientific notation. There are several advantages to scientific notation. One is there's really no limits. We're not going to come up with numbers too big or too small, where scientific notation is inadequate to describe it. Now, I said in kind of regular problems, the way we think of numbers, there actually are real problems where we could come up with numbers far bigger than the number of atoms in the universe. The biggest number that I can really conceive of having any meaning, I'm going to write this down. That is 10 to the 123rd power. This was a number that was calculated by a guy named Roger Penrose. And it's kind of like the number of distinct universes that could even exist. The way I kind of visualize it, if you had this many universes and you tried to create another one, it would have to match something that had already been in this collection here. Like if you just moved on, like if you had say you had all these universes, they're all unique. So like there's something different about each of those. Now if you created another universe and just tried to make it different, it would be impossible. Or like if you took one of these universes and just moved an atom over a tiny difference, it would be identical with a different universe. It's kind of an intuitive and not very precise way of visualizing like what this number could even represent. But like this is 10 to the power of 10 to the 123rd. This kind of double exponent thing, which does show up in like one branch of physics called statistical mechanics. When you deal with like all the possible states something could be in, you sometimes come across double exponents, but that's definitely not something we're going to worry about here. So as far as we're concerned, any number we can easily handle with scientific notation. So that's one big advantage. Another advantage of scientific notation is when it comes to calculations. Like, I'm going to write down two numbers. Mass of the sun I'm going to write it. I wrote down, here, I'll write down a little bit precisely. Mass of the sun and the mass of the earth okay, so we've got these two numbers, mass of the sun, mass of the earth, written in scientific notation. And if we want to calculate the gravitational attraction between the earth and the sun, we're going to have to multiply these numbers together. Now that won't give us a force. We'll have to do other things to it as well, like take distance into account. But just one part of the process, we're going to multiply these two numbers together. So how do we do this in scientific notation? It's one of those rules in algebra. I think it's called the associative rule. Or no, the commutative. It's one of those anyways. I forgot what they're called. Yeah, I think that's, well, whatever it's called. So I say you have three numbers and you want to multiply them. You know, we have rules for just multiplying two numbers at a time. So what do we do if we have three? Well, it doesn't matter. You can multiply, like, say, A and B together and get a single number, and then multiply that by the other number, and you'll get your answer. Like, let's just do a concrete example. I don't know why we're even doing this. Maybe not necessary. But here, if we want to multiply this, you can say 2 times 3 is 6. And 6 times 6 is 36. If you do it the other way, 3 and 6 is 18. 18 times 2 is 36. You can multiply in any order. And so we can do that with scientific notation. Like here, we're multiplying, if we multiply the mass of the sun and the mass of the earth, we're multiplying 4 things numerically. We also have units. But I'll write it out. Let's do the mass of the sun first. Okay, so we can rearrange the order however we want. So we can do this. We can say 1.99 times 5.98. Take care of these two numbers. And then we have 10 to the 30th times 10 to the 24th. And we also have a kilogram times a kilogram, so there's a kilogram squared. Okay, now again, multiplying these two numbers might have looked a little bit intimidating, but you can practically do this in your head. 1.99 times 5.98, that's around 6. Now 12. So like 2 times 6 is 12, and 10 to the 30th times 10 to the 24th, that'd be 10 to the 54th power squared. And if you want this in scientific notation, well, let's talk about that in a minute, but you can see how easy it is to do this calculation. If you want a little more precisely, you can multiply these two numbers. Yeah, not that complicated. We'll probably round off to 12 anyways. And so working with scientific notation is really nice mathematically. That's another big advantage to that. You can just even without writing it all out, you could almost do this without, just in your head without looking at it. Okay, 2 times 6 is 12. So it's, 11.9 something because, let me just do that. Here, 5.98 times 1.99. Yeah, it's 11.9, but we can round that off to 12. And then 10 to the 30th and 10 to the 24th, multiply those, you get 10 to the 54th, and done. So very, very nice to work with calculations in scientific notation. That's a great advantage to it. Now this number, the result is not in scientific notation. So how do we convert this to scientific notation? And what we have to do is we have to move this decimal point over to the left one. So in scientific notation, you always have one digit and then a decimal point and then the rest of it. So in order to move the decimal point to the left, we have to divide this number by 10. The problem is if we divide this number by 10, well, we're changing it. And so to compensate for that, let's multiply by 10. So we had this number by itself. If we divide it by 10 and then multiply it by 10, we're not changing anything. These two operations undo each other. So doing this, we can say this is 1.2 times 10 to the 54th. And then times 10. But again, multiplying by 10, that just adds 1 to this exponent. So we have 1.2 times 10 to the 55 kilogram squared. So that's another great advantage of scientific notation. And there's one more fairly significant advantage to scientific notation, which I want to talk about. Here, let's erase this. Let's clear the screen. And let's look at kind of a simple problem. Let's say speed is distance over time. All right. So let's say you want to know how fast something is going. How would you determine that experimentally? Well, you could measure the distance it travels in some time interval and just divide them. So let's say an object travels 10 meters, and it takes 3 seconds to do that. So its speed is 10 meters over 3 seconds, which is 3.33, repeating of course, meters per second. So the question is, how fast is this object moving? Seems like we have the answer right here, but we wouldn't want to write this down because this is complete nonsense. Why is this nonsense? Did this object actually travel 10 meters? And the answer is no. These are things that we are measuring, and all measurements have errors. So what happens if one of these numbers is a little bit off? Like, let's say instead of 10 meters, it only traveled 9.5 meters. It's easy to make a mistake like that if you're doing a crude measurement, just being off by half a meter. So let's look at example 1. Say the speed, I'll just write s. Let's say if we measured it more accurately, instead of being 10 meters, let's say it was 9.5 meters in that same 3-second interval. Oh, here, 9.5 over 3. I think that's what it is. Oh no, it's here, this. That's repeating. Okay. And so again, we're trying to measure the same thing. Say one person measures it without much accuracy, gets 10 meters. Someone measures it with a little more accuracy and gets 9.5. These numbers are different. And again, every time you measure it, you should get something a little different because of errors. However, the first number, they definitely agree on the first number. Not so much on the second one. And if they can agree on the second number, then this third one, this 3 here, do we have any confidence in that at all? No, of course not. Like if we don't even know if the second one is a 1 or a 3, maybe it's a 2. If we don't know what the second digit is for sure, we don't even want to guess what the third is, most of the time. And so what we would probably do in this case is say the speed, just based on the information we have, probably say 3.2 meters per second. And just leave it at that. because this 3 we're pretty sure about. They both agree with that. The 2, the second digit's not so sure, but 2 is kind of like in the middle. So that would be reasonable to say we're not claiming that 2 is exactly correct, but that's like our best estimate for that. And if this is an estimate, we definitely don't want to write anything beyond that because, that's completely unknown. Now, there are extreme cases where you can have like an uncertainty that actually does contain 2 digits, but that's typically if you're doing extremely precise experiments. Not something we're going to consider here. So typically when you have one thing that's a little bit questionable, what comes behind that? Complete mystery. So we don't want to even write that down. Okay, but this is where we're looking at 2 different measurements and trying to estimate what the actual, or what our best estimate for a reasonable answer is. What if we only have one measurement? What if this is all we have? 10 and 3, then this is our answer, but we want to have some way of knowing just how significant, like how much confidence do we have in each of these numbers. And we use something called significant figures to give us, they're really more just guidelines. We don't want to necessarily take them too far. Like, don't take them too literally, like this is exactly correct. Just think of these as guidelines. Like, how would you write your answer? You want to give like an honest answer that, is like your best estimate for this number. And so what we do is we have this idea of significant figures, where actually I want to move on to a different example than this because we started by talking about scientific notation, and one of the advantages is when it comes to significant figures. But the example I wrote down is kind of the problem, the case where we can come up with an issue. But significant figures, these are basically, you want to write down, let's say I make a measurement. Let's just say some length. And let's say I claim that this distance is 4.56 meters. What I'm saying is I have confidence in these numbers. I believe the 4 and the 5 are right, and 6, I'm not sure that number is a 6. Maybe it's an 8 or maybe it's a 3, but this is my best estimate for that third digit. And so we have to understand when we write numbers, we want to give some information about how precise this measurement is. So if I write 4.56, I believe in these numbers. This one is an estimate, but the other 2 I'm pretty confident about. And we say this has 3 significant figures. I'll just write SF for significant figures. Okay. And then let me give you another example. Let's say X is 0.00014 meters. This number has 2 significant figures, the 1 and the 4. Now what about these zeros in front? These are just placeholders. So like we're measuring something, I could convert to a different unit. I could say 140 micrometers, something like that. And so like changing units or something, moving the decimal point around doesn't affect the number of significant figures. So here we just have 2 significant figures, the 1 and the 4. Now these are both, we can call these just both clear examples, where you can just look at the number and tell how many significant figures there are. Now what if I had another number, 100 meters. Now, how many significant figures does this number have? This is what they call an ambiguous case. You can't tell just from looking at this number how many significant figures it has. It could have 1, 2, or 3. Now, most likely it would have, like, say, one significant figure. See, if you have one significant figure, you just write down the first digit. It doesn't have to be a 1 here. Maybe, let's say 400. Doesn't matter what that number is. So, but here, we've got this digit here, and then nothing after it. So this is one significant figure, but we have to write these zeros here just because it's 400. It's not 4. We can't just write down the first number and forget about the rest, because we need, these two as placeholders. And so it probably has one significant figure, but what if you actually have two significant figures? So like the 4, and like the second one just happens to be 0, and then you have a placeholder behind it. So like, what's that doing there? Like, is this number just a placeholder? Do we know what it actually is? We can't tell just from having it written like this if these are placeholders or actual significant figures. So it's possible we got 3 significant figures. And so how do we communicate that information about the number of significant figures? And there's various ways of doing it. One way is just literally like this. Say 400, and then you can say there's 2 significant figures here, or 3. Another way, sometimes you can put like a line, like if you write it like that, like this 0 is significant, this one isn't. Or if it was 3 significant figures, that would be simple. Then you just put that decimal point at the end. So different ways of doing it. You might see something like this. Let me write this a couple times. Let's write the number 400 with 1, 2, or 3 significant figure. So 1 significant figure, we write the 4, and then we have 2 placeholders because we have to. For 2 significant figures, you'd often see it written like this. You can see it like 40 with a decimal point here times 10. And so like you can see this is 2 significant figures and then multiply by 10. So it's 400, but this way at least it's clear how many significant figures you have. I don't like how this one looks. I would rather just write 400 and say there's 2 significant figures, but you'll see this written. And with 3 significant figures, you can do this. Now what's great about scientific notation though, is there's never any ambiguity, because you always have 1 digit, and then the rest comes after the decimal point, so you don't need to add placeholders. So again, writing 400 in scientific notation, we'd either do it like this. We could say 4 times 10 squared meters, 4.0 times 10 squared meters, or 4.00 times 10 squared. You can just immediately see 1 significant figure, 2, or 3. Like if you only want 2 significant figures, why would you bother writing that extra 0? There's an infinite number of zeros. You can pick however many you want. So you can just use that to get rid of that ambiguous case. So that's another advantage of scientific notation. You never have to worry about the ambiguous case. Now, students often ask, how important are significant figures? And the answer varies from extremely to not at all. Conceptually, very important. You really need to know, like in this case, say 10 meters over 3 seconds. This is not 3.333 so on meters per second. So that part is extremely important to know. When it comes to like practical matters for this class, if you get significant figures wrong, am I going to take points off? And no, I don't generally do that. I decided to do that one semester, just consistently grade everything, getting the right number of significant figures, and everyone got really mad. And yeah, it's probably not worth the effort. So what I do is if a student has a problem getting this concept, where you constantly write things with 6 or 7 significant figures, which is very unrealistic. I'll just make a note, watch significant figures, but I don't take points off. So I generally don't. I'll leave that option open, but it's been years since I've done so. So, I might mention it, but because it is an important concept. But one reason I don't really emphasize it too much, well, I guess 2 reasons. One, this is a general science class, so you're not going to be engineers, where things like this can be extremely important. But another reason, well, let's look at, how would we determine how many significant figures that we should have? And there's 2 rules the book talks about. There's multiplication and addition, or multiplication / division, or addition and subtraction. So these are 2 operations. So let's say we multiply 2 numbers. Let's say 320 times 11. All right, let's multiply these. Well, okay, so if we just multiply them, we get 3,520. Now, let's look at the number. Now, the principle that applies here when it comes to multiplication and division is kind of the weakest link principle. So, maybe I didn't make a good example here because both of these numbers have 2 significant figures. So let me just change this a little bit. Just so we have 3 significant figures on the first number and 2 in the second one. Now we got a number here, of course. Okay, 3,531. Now the question is, how many significant figures does our result have? And the weakest link principle is in this case, the weakest link is 11. There's only 2 significant figures here. And so if this only has 2 significant figures, our final answer should not have more than 2 significant figures. So what we would write down is just 3,500. So that would be the answer that we would write down. And then whatever units this is. So what did we do with the 31? We just ignored it. Now, we don't necessarily just ignore it, because if we did a different calculation and got, say, 3,591, then we would round up and write 3,600. So you use the standard rounding rules, 5 and above you round up, or below you round down. And so rounding this off to 2 significant figures, 3,500. Again, it makes sense that the weakest one, let's go back to our distance and time example. Let's say that when it comes to measuring time, we can only get, let's say we get 2 significant figures here. That's the best we can do. Now, when it comes to measuring distance, there's really no point in going beyond 2 significant figures, or not much of a point anyways. You don't want to go too far beyond that. Because, say that you could measure this, to 8 significant figures. Some crazily precise calculation. If there's a big error in time, you're not going to really improve your result by going through all that trouble of measuring this one number by 8 significant figures if another one only has 2. Because whatever uncertainty there is in time, that's going to affect the speed. And so, your answer is going to be imprecise. No matter how precise one number is, if one of them is off, that's going to affect the final result. that'll kind of determine just how precise the final answer can be. Okay, so that's when it comes to addition or multiplication and division. Use that weakest link principle. Your final answer should not have more significant figures than the least significant of whatever went into it. Okay, now addition and subtraction. Let's add these two numbers. Okay, now here we don't worry about the number of significant figures. We only care about like where they are. So first, let's just add these. So we add it up, and we get 3,910.4. Now, this number is obviously very precise. There's 4 significant figures. This one's only got 2. So what I mean is, this number is unknown. Like this 4 here, we can kind of look at that as a good estimate, but this next number, no idea. And so, if we don't know what this number is, remember this digit here came from adding, like we know this one is a 1, but this could be anything. We don't know what it is, so if we don't have confidence in this number, we don't really know what that one beneath it is either. So the answer to this addition problem would be 3,900. So like this digit, we ignore. And so, yeah, we have rules for determining based on, like, if you're reading a book and a problem, and that made no sense. If you're reading a problem from the book, they'll give you the numbers to plug in. So here, let's say you travel 151 meters in 2.2 seconds. So you can easily do this calculation. Let me just do that. That'd be 68.636. And it goes on, but I don't care. So you're given the information, so you typically know the number of significant figures in these problems, and you have rules for both addition, subtraction, multiplication, and division. So here we can see 3 significant figures. This one's only got 2. So in this case, we'd round it off to 69 meters per second. Because this one, 6, we round up. So that would be the correct way to answer this. But again, mention one reason I don't emphasize this too much, getting like that, exact. Like if someone said 68.6, am I going to take points off? No, because, again, I mentioned we're not engineers. But also, there's another issue that the book completely glosses over that very much applies to this class. And let's say we have something like this. Let's say we have a building. So here's a building with an unknown height h. And we want to know the height of this building. So we get a protractor. You might have seen these with like a hanging string. So you have a weight just so the string is vertical. And you have like a rod with a protractor attached to it and a hanging string with a mass, so it's just kept vertical. And again, if you lift this object up, the string is going to remain vertical. And you can use a device like this to measure the angle. So like if you're standing here and you point so that you're kind of aiming at the top of the building, you can measure this angle using the protractor. So let's say we come up with an angle of 27 degrees. And we can measure, say using a tape measure, the distance along the ground. And now say we want to know the height of this building. where we know D is, say, 10 meters. So we measure a distance 10 meters from the building, use some kind of simple device to measure this angle, and then let's find the height of this building. Now, this is something we'll review if you've never seen this before, although pretty sure everyone has. We can say just based on this triangle, tangent of theta is h over d. Or h is d times the tangent of theta. So in this case, we have 10 meters times a tangent of 27 degrees. Now the problem is 27 has some errors. So it has significant figures as well. And so how do you deal with trig functions? And that's complicated because there's no simple guidelines for that. It would actually depend on this angle. Like using the same kind of precision, if you have like a small angle versus a big one, the number of significant figures you keep could vary significantly based on the value. So there's no like simple guideline you can just remember and use. And so the book just says all angles have 3 significant figures. So they're kind of just avoiding that problem. So I view significant figures simply as guidelines that are reasonable, and typically for the kind of problems we do, the number of significant figures should be limited to, maybe 2 or 3. Don't go beyond 3 unless you have a good reason, though. It would be kind of difficult to do an experiment to get like 3 or 4 or like 4 significant figures. Yeah, that would take a lot of work to measure something with that kind of precision. So, general guideline, just 2 or 3 significant figures. And if you do that, then I'm happy. Okay, so I think that'll be it for this, this video. Next, we're going to talk about conversions. But we'll do that in a separate video.